Okay, so today's video is a follow-up to the VSEPR structure exercise that you did as a virtual lab. And so what we're going to do now is we're going to talk about some of the ramifications of molecules having three-dimensional structures. So molecules can be classified as polar or nonpolar, and the source of that polarity is polar covalent bonds. So let's define those right now. A polar covalent bond is a covalent bond between an atom with a low electronegativity, so this is typically hydrogen or carbon, and a high electronegativity. That's typically oxygen, nitrogen, fluorine, chlorine, and sulfur. There's a quantitative definition for a polar covalent bond. It's when the electronegativity difference on the Pauling scale is 0.4 units or greater. So that would makes carbon-hydrogen bond just less than polar. So we consider carbon-hydrogen bonds to be nonpolar bonds. But when you bond either carbon or hydrogen to any of those other elements that I already mentioned, you get a polar covalent bond. So let's look at a classic example, which is the hydrogen fluoride molecule. So what we've done here is we've taken a space-filling picture of a hydrogen fluoride molecule, kind of a 3D model, and we've colored it according to the charge. And so blue colors are more positive and red colors are more negative. So what's happened here is that the very electronegative fluorine atom has polarized, that's the source of the word polar bond, to polarize the electron density in the covalent bond. So although that pair of electrons between the hydrogen and the fluorine is technically shared, since the fluorine has a much higher electronegativity, they spend more of their time around the fluorine than they do around the hydrogen. And sometimes it's said that these bonds have partial ionic character. So they're somewhere in between a covalent bond, a pure covalent bond, and a purely ionic bond, since the fluorine is dominating the time of those shared electrons, or sort of the space where those shared electrons are can be found. All right, so we can I talked about this already. If the difference between the electronegativities are greater than 0.4, we call it a polar covalent bond. And so the false color scale that we have here is shown on this, with the partial positive charges being shown by this little symbol here. That's a Greek lowercase delta, partial positive. Sometimes you'll see that. And there's a partial negative with the red colors. Okay. The way that we draw a bond dipole to indicate that a polar covalent bond is polar, when we're just drawing Lewis structures or other representations of three-dimensional models and we don't have access to false color, is we put a positive sign at the end that has the partial positive charge, and we draw an arrow pointing towards the end with a partial negative charge, and that's basically just showing which direction the electrons are pulled towards. And so we call that a bond dipole. All right. Okay, so polar molecules are molecules that have polar covalent bonds. But that is not a sufficient condition for a molecule to be polar. It has to have polar covalent bonds, and when you add up the magnitudes and directions of all of the polar bonds in the molecules, it has to not be zero. Okay, so that's when we talk about something called vectors. A vector is a magnitude and a direction, and so when you add those things using a mathematical method called vector addition, they can partially cancel, they can add to each other, so it gets bigger, but that result is called a resultant, and it can't be zero if a molecule is going to be polar. So I'm going to do 4 examples, and it should be completely clear by the end what I mean about that resultant being zero or not zero. So if it's going to be a polar molecule, it's got to be non-zero. That means when you add up all of those arrows pulling in different directions, there has to be something left over. Okay, so let's consider our first example, water. Water is the quintessential polar molecule. It is a polar solvent. So one thing that we'll talk about in a future chapter, in which I think you've heard me mention before, is that you have the idea of a polar solvent, and that means polar molecule. Water is made up of polar molecules. Okay, so why are they polar? Well, if you look at what we have the low electronegativity hydrogen atoms connected to the high electronegativity oxygen atoms. So that means we're going to get a partial positive charge on each of these hydrogens and a partial negative charge on the oxygen. And we can use our dipole notation to show that. So we put the positive charge on the hydrogen and we draw the arrow towards the oxygen, and then we repeat that on the other side. Now, if you look at these arrows, they both point towards the oxygen, but because the structure of the water molecule is bent, this is where the VSEPR comes in. In order to be able to know how to do this, you have to know the structure. If you had predicted a linear structure for the water molecule, of course that would be incorrect because it has 4 electron domains around the central atom, and we learned in the VSEPR lab that anything with 4 electron domains around the central atom is going to have a tetrahedral arrangement of those domains. And so that means that these bonds do not exactly cancel. That means there's something left over, and when we add them up to get the resultant, there is going to be a net dipole moment pointing this way. So on the side that has the hydrogens, there's going to be a partial positive charge, and on the side that doesn't have the hydrogens, there's going to be a partial negative charge where those lone pairs are. And so that is going to be the net dipole moment of a water molecule, and that's why it's a polar molecule, because those two vectors, those two bond dipoles, didn't cancel out when we added them together, and we're left with something. And we can do another example. If we do a molecule here called trichloromethane, don't be concerned about knowing that name, it's not important, but it's a carbon atom with 3 chlorines attached to it and 1 hydrogen. And so if we think about the bond dipoles here, there'll be a very small one for the hydrogen-carbon bond, right? Technically, there is a difference. Hydrogen's 2.1, carbon's 2.5, so there is a very small bond dipole there, and there's a much bigger one with the chlorine. Chlorine's got a electronegativity of about 3. Okay, and so we're going to have now the carbon's going to be the partial positive, so we're going to have equal dipoles pointing towards each of these chlorines. Okay, and you can see here that I've used this wedge and dash formalism to show the three-dimensional structure of, let me back up here, three-dimensional structure of the chlorines, right? So this chlorine and this hydrogen are in the page along with a carbon atom, and then this chlorine is coming out of the page, and so that's why you can see it's got this wedge. So the big end of the wedge is supposed to be closer to you than the skinny edge, and then this dashed wedge, you see the bigger end is attached to the carbon and the smaller end is attached to the chlorine, and that indicates that this chlorine is pushed away from you into the page. So these are kind of equal bond angles, with this one coming out, that one going away, and this one in the plane of the page, and they're all down, they're all below the carbon a little bit. And so if we add up those bond dipoles, they're all going to kind of point down into the page. That's going to add to this bond dipole, and when we do that vector sum to get the resultant, we are going to get this red arrow. Okay, so the point here is that you can clearly see by looking at these directions. If you can't clearly see, you need to stare at it until you do see it, that these arrows do not cancel each other out, rather they add up, and that means that you are going to get a non-zero dipole moment. So therefore this molecule, trichloromethane, is also a polar molecule. So now we can consider nonpolar molecules, and there's a couple of ways to get them. The first way is you can have a molecule that just doesn't have any polar bonds in it. Clearly that kind of molecule is never going to be polar. Or you can have a polar molecule where when you add up all of the dipole moments associated with the individual bonds, the bond dipoles, they exactly cancel each other so that there's no resultant, and that means that the molecule itself is not polar. And the classic example of this is carbon dioxide. So now when we look at the carbon dioxide Lewis structure, we see that there's only 2 electron domains around that central atom. Each double bond counts as 1 domain. And so since there's only 2, we know that those are going to be 180 degrees apart, and this is going to have a linear structure. Now carbon is not electronegative and oxygen is very electronegative, and so therefore we are going to have dipoles that are equal and opposite. So they're both between the same atoms and they have exactly opposing directions. So those 2 dipole moments are going to cancel out exactly, and carbon dioxide is a non-polar molecule. So that's the way this works. You have to know the 3-dimensional structures of the molecules. Are they bent? Are they linear? In order to make the correct predictions about whether something is going to be polar or non-polar. Okay, and here's the last one. If we replace that hydrogen at the top with a chlorine, we have that same tetrahedral structure around the carbon, right? So we've got these 3 chlorines, and they're in exactly the same locations as they were here, but now the top atom is also a chlorine instead of a hydrogen. So this is carbon tetrachloride, and so we've got the same 3 bond dipoles for the lower 3 chlorines, and now the upper one has the same bond dipole just pointing in the up direction. And because a tetrahedron is very symmetric, all of these things are going to cancel exactly, and carbon tetrachloride is a nonpolar molecule, just like carbon dioxide was a nonpolar molecule. So this is one of the uses of knowing the 3-dimensional structure. So we can predict the properties of solvents, we can predict the properties of molecules, we can predict whether or not a molecule is going to dissolve in another molecule, right? So if you have a waxy substances that are waxy, they repel water. Why do they repel water? Well, waxy substances have all nonpolar bonds in them. They tend to have lots and lots of carbon and hydrogen bonds and no electronegative atoms in them. And so that means that when they come into contact with water, it's a different substance. Water's polar, wax is nonpolar, so that's why water beads up and rolls off of wax, and it doesn't want to mix with it. But if you have something like a solvent, a non-polar solvent that you can use to get wax off of something, off of your hands, now that will dissolve it. The 2 things will want to mix. So the rule for when you have polar substances and non-polar substances is that like dissolves like. Polar things like ionic compounds are very polar, right? Because you've got a positive charge and a negative charge. It's not partial positive and partial negative, it's full positive and full negative. So that's why water is such an excellent solvent for dissolving ionic compounds, is because water is a very polar solvent. Okay? So non-polar solvents will dissolve non-polar things. Polar solvents will dissolve polar things, and if you try to mix a polar solvent like water with a non-polar solvent like gasoline, they don't mix, right? Oil and water don't mix. It's so well known and so well understood that it's even a cliche. So you can predict general properties of chemical compounds by understanding this very detailed low-level atomic structure of the molecules, of how they're made up. So we go with the Lewis structure and figure out how they're connected with single and double bonds. VSEPR allows us to predict the 3-dimensional structures of those molecules, and then knowing about the differences in electronegativities and which direction the different bonds are pointing allows us to make a prediction of whether or not those molecules will be polar or nonpolar. And so then we can predict macroscopic properties we can see. Certainly you'd be able to tell with your hand if something was a waxy substance or not, whether it felt slippery. Okay. All right, so you have a assignment associated with this. It's not a discussion question. It's actually a short homework for you to do from problems in the textbook. So please do that now.